This conference will now be recorded. This conference will now be recorded.
Very good evening, students. Today we will be continuing the discussions on PYQs on the paper JEE Main 2021 31st August Shift 1. So we had already discussed few problems from the 11th part in the previous class. So in today's class, I'll be focusing on the questions from the 12th portion. Okay, we have few very important and good questions in this. Let us try to solve the problems. Okay, so
This conference will now be recorded.
very good evening, students. We have been discussing PYQs from the JEE Mains papers. Today we'll be continuing the discussions on the paper 2021 31st August Shift 1. In the previous class, if you remember, we have solved questions from the 11th part. Today we'll be focusing on the 12th part. Okay, the questions from the 12th part. So the first question you see in the screen, we'll start our discussions with this. So the question says a coil having n turns is, this is wound tightly. Okay, this is not wound tightly in the form of a spiral with inner and outer radii A and B respectively. Find the magnetic field at the center when a current I is passing through the coil. Okay, so let me try to explain you this question. See, there was, suppose, a wire, long wire, and it is wound tightly like a spiral, like this, tightly. Okay, wound tightly like this. So this is kind of a spiral, and the inner radius, suppose this is A and the outer radius is B. Okay, now if current I is flowing through this wire, then what will be the magnetic field at the center? Let me show you the situation. So this is the situation. Okay, so this is the inner radius, okay, A, and this is the outer radius of the spiral. Now you have to find out what is the magnetic field at the center. See, we know magnetic field for a circular coil, right? We don't know for a spiral, isn't it? We don't know for a spiral, but we know for a circular coil. So we will be, for simplicity, we'll take this, or for the sake of solving this, we'll just take this as very closely spaced concentric circles, kind of this. Look, this one. Okay, for simplicity, we'll just consider this spiral like this. Okay, and see, we know the magnetic field at the center due to a coil, sorry, due to a coil having a single turn, or if I take n turn, mu 0 Ni by 2r, right? Mu 0 Ni by 2r. So this is the magnetic field at the center for a single coil. What is this r? R is the radius of the circular coil. N is the number of turns and I is the current flowing through that. So if suppose I consider, see, I'm considering at x distance from the center, common center, x distance, I just consider at a x distance having, see, I'm just taking this particular portion. I'm just taking dx thickness of this spiral, ds thickness of this spiral, dx thickness of the spiral at a distance x. Okay. So what I'm doing, I'm doing, okay, let me write. Let us consider dx thickness at a x distance from the center. I mean, I can just consider a ring, kind of ring having thickness dx. Okay. Now I have to find out how many number of coils or how many number of turns will be there in that dx thickness, because I know magnetic field, if I write for this thickness, so what I have to write, dB, magnetic field dB is equal to mu naught by 2x into the number of turn here. Let us say number of turns will be some dn. So what is this dn into I? I have to find out what is this dn, number of turns. See, total number of turns are n. So number of turns per unit length will be n by, or unit distance will be n by b minus a. This is the number of turns per distance, okay, or per unit length, okay, per unit length or distance from the center. Now if I have to find out number of turns dn within this thickness, then I have to multiply the thickness of that. Okay, so this is the number of turns. So what will be the magnetic field due to this particular region? Okay, or uh, the ring or the region, circular region I'm just taking, having thickness dx and radii x. So for that elemental ring or elemental coil having thickness dx will produce magnetic field this much, where dn will be, so mu 0 dn is n divided by b minus a into dx into I divided by 2 into x. Okay, so this is my magnetic field due to this particular region or particular circular ring having this many number of turns. So what will be the total magnetic field? See why I am taking this dx, because it is continuous distance, since these are tightly wound. Okay, the wire is actually, or coils are actually tightly wound. Okay, so that's why I'm taking continuous region. Now look, if I have to get B, total magnetic field, I have to integrate this over Cx is equal to A to B. Okay, so then look, I have mu naught n b minus a. This is a constant term and current is also constant. So what I have, so 2 here I'll multiply. What I have dx by x, where the limit of x goes from a to b. So it will be mu 0 n I by 2 b minus a. This will be ln, or you can take log ln e base. See, there is an option. So ln e means log of e base. So ln x will be b by a if I put the limit, right? Ln b by a. So this option number B will be the correct answer for this question. So this was really a very good question. Okay. So what is the key concept? Key concept is that you cannot just take this as a circular coil. You have to actually find out the number of turns in a particular, like in between this. Okay, so number of turns you have to take. Here, see, we have done just the integration on the number of turns itself. Okay, that is space varying. Okay, all right, so this is the point you have to remember. Okay, so now we'll go to the next problem. This problem is very simple problem. In an AC circuit, an inductor, a capacitor and a resistor are connected in series with XL and XC is equal to R. That means capacitive reactance and inductive reactance are equal to R. Okay, the impedance of the circuit. So impedance, we know it is square root of R square plus XL minus XC whole square, right? This is the thing we know. Now if this XL is equal to XC, then this term goes to 0 and we get Z is equal to R, and this happens only at the resonance condition. Okay, this happens at resonance. The whole power will be dissipated through the resistor. So this occur at the resonance. All right, so the option B will be the correct answer for this question. Now we have question from modern physics. A moving proton and electron having same de Broglie wavelength. So same de Broglie wavelength, a proton and electron both has the same de Broglie wavelength. If K and P denotes the kinetic energy and momentum respectively, then choose the correct option out of this 4. So we know lambda is equal to h by p. Okay, since wavelengths are same for both of them, this momentum, linear momentum is going to be same. Okay, so I can say linear momentum of proton will be equal to linear momentum of electron. So this part is fine with momentum. But what about kinetic energy? Kinetic energy we know p square by 2m. So from here also I can say, or you can just apply this p is equal to h by lambda, that you can write here. So h square by 2 lambda square. See, this lambda is constant, h is same for both, but this mass is different, right? So this is, see, kinetic energy is inversely proportional to the mass, and proton has got little higher mass than the electron. Therefore, we can say the kinetic energy of electron will be greater than the kinetic energy of the proton. So Ke is greater. K is greater. Okay, so option C will be actually the answer for this question. Okay, so this was also a very simple problem. Now we have this problem. What is this problem saying? This problem saying, consider a galvanometer shunted with 5 ohm resistance and 2% of the current passes through it. What is the resistance of the given galvanometer? So let me draw the galvanometer. So there will be an associated resistance, that is Rg, say, and when it is shunted with a resistance Rs, then most of the current will pass through this. Let us say the current is Is through this Rs and current through this is Ig. Okay, so we can write Ig is equal to Is. Sorry, Rg Ig is equal to Is Rs. That means the potential across both of them will be the same. This I can write. Now let me see what are the informations given here. Rs is given as 5 ohm. This is 2%. Suppose there is current I, total current I, 2% of that is passing through the galvanometer. That means, let me take Ig is equal to 2I by 100 into Rg, and see, I minus Ig will be actually Rs. Okay, then I can write 98 by 100 is equal to Rs, sorry, into Rs. Now I have to find out what is Rg. This is I. So this I can cancel out. This 100 I can cancel out from both. So Rg will be 49 into Rs. So what is Rs? Rs is 5 ohm. This will be in ohm. So this will be 245 ohm. Okay. So this was really good question, but not very tough also. So option C will be the correct answer for this question. Now let us see this question. What is this question saying? This question is saying the following circuit, logic circuit, the sequence of the inputs 0, 0, 0, 1 and 1, 0 and 1, 1. The output Y for the sequence will be. Okay, so we have to basically draw the or write down the truth table for this. So this is A, this is B, and say this is y. So I have first a, then what is the output I have to write? A B 0, 0, 1, and then 1, 0, and 1, 1. Okay, for this I have to like write down the truth table. So first of all, let us just find out what is y. To, to find out y, let me take this as y1 and this as y2, and these two will come here, right? So what is y1? See, y1 and y2, if we find out, say a b, that means this is and, okay, this is and operation, so this will be a and b. Now what is this? This is or operation, this will be a or b. Now this is actually NAND operation, okay? So what is NAND operation? So this will be and, see, y1 and y2, so in between and operation and whole bar of that. So this will give you, if you apply De Morgan's theorem, this will give you, you can actually get separate, see, y1 bar, and in between there will be or operation, a plus of b, like a or b whole bar. Okay, now this is fine if you want to keep, otherwise you can write a or b separately. Okay, and this thing you can write separately, a and b bar, okay, like this, if you want to keep like this. Okay, so since there is or operation, let me further simplify a or b and this term. Okay, further I have b bar or a bar and b bar. Let me do further. See, if I take a bar common, then I get a, see, 1 plus b bar, so that will be 1. And next, if I take b bar common, 1 plus a bar, see, 1 plus of anything, 1 or anything, so this is already high. If you put 1, then also you'll get 1. If you put low, this a to be low, then also you'll get high output, so this will give you 1. So ultimately I get a bar or b bar, a bar or b bar. Okay, so now let us see. So a bar or b bar, that means if I put 1, sorry, a to be 0, a b both 0, both are 0, that means 1 and 1, 1 or 1, you will get 1. If you put a 0, then you get, see, if one among them is low, you will get output. Here also you will get output. But if both are high, then you get 0 or 0, so you get low output. So 1, 1, 0, that is this one will be the correct answer for this question. So this is very, very simple. See, there is another method to do this. If you can't apply De Morgan's theorem for simplifying this circuit, logic circuit, there is another way to do. Let me just give you some hint of that. See, you have a, you have b, you have y1, you have y2, okay, this one, and finally you have y. At least you should know y is equal to, let me just clean this portion. If somebody doesn't know De Morgan's theorem, how to tackle this kind of circuits, for that case you have to actually write all these outputs in between also. So I have 0 0, so for y1 it is 0, for y2 it is 0. Let us keep like this up to here. Then for 0 1 0 1, so AND operation, y1 will give you 0, OR operation give you 1. Then 1 0 1 0, AND operation will give you 0, OR operation will give you 1. Now 1 1 1 1, both will give you 1. Okay, now you have got, see, two inputs for this y, for the last gate. See, now I can actually erase this portion, so you don't have to think of this part now. You have these two inputs and you have y1 and y1 and y2, then whole bar. Let me see, y1 and y2, if both are 0, then AND will give you 0, but inverse of that or bar of that will give you 1. Now this AND operation 0 1 will give you 0, a low output, but bar of that will give you 1. For that, this one will give you, AND operation will give you 0, but a bar of that, see, 0 bar means 1, 1 bar means 0. So AND operation will give you for 0 1, sorry, 1 0, let me, okay, so these are both 0 1 0 1, so this also will be 1. But if you have 1 1, then your AND operation gives you 1 and bar of 1 is 0. So this is, see, you are getting the same answer for this. Okay, so dear students, if you can apply De Morgan's theorem, that is very fine. If you cannot, then you have to go with this. Okay, intermediate outputs also you have to write in the same truth table and then apply these operations, at least the basic operations you can know. Okay, all right, so next problem is this one. Let us try to understand this problem. Is very simple problem, but we have to understand it. So a sample of radioactive nucleus A disintegrates to another radioactive nucleus B, which in turn disintegrates into some other stable nucleus C, stable nucleus. That means C is not breaking after that or disintegrating. Okay, plot a graph showing the variation of number of atoms number of atoms of nucleus B versus time. Okay, so you can see this is exponential graph. This is kind of, so in the initial it is increasing, then decreasing. This is constantly increasing for some time, then it is constant, number will be constant, then see it is also increasing with a constant slope, okay, or constant rate. After that it is exponentially decaying. So what we have to find out, see, I know, see, A will be disintegrating. Okay, A will be disintegrating in this, right, lambda T, with this kind of formula, right? Then I'll get B, isn't it? I'll get B. Okay, I'll get B nuclei. But see, in the beginning I will not have any kind of B. just after decaying only you will get this. So this I can actually strike out, because initially it is showing a very large number, where I know B will be 0 initially. So B, number of B nucleus will be 0 initially until the decay occurs. Okay, we'll get 0. So all these three are showing 0. Now the thing is that after decaying you are getting B, and B also starts decaying. Okay, B also starts decaying, but initially you know the decay rate of this, because it has already started decaying. After production of B only it will be decaying. So by the time it starts decaying, the number of B atoms will be actually increasing. Okay, B will increase, B will increase. Okay, because one by one this nucleus will be generated by decay of this A, right? Now it has also started to decay, but by the time it starts decaying you will have a good enough number of B nucleus. Okay, further when it starts decaying, what happens actually, there will be a time when production of B and decay of B will become equal. At that time this will not increase, the number of B in produces and immediately start decaying. So you can understand that for some time the number of B will be increasing from 0 to some number, some B prime number, and B prime, see, B starts decaying itself, but there will be a time until when the production of B and the decay of B are not going to be equal. Till then we'll see increasing slope of the nucleus of B, and thereafter it will be constant. That means there will be constant for some time, just for some time, very negligible time, and therefore it will thereafter it will decay. Okay, so you look this option B, see, it is increasing. At some time it is actually becoming equal. So that is the time when the maximum B will be there, just before becoming this rate of production and rate of decay equal. Just before that it will be maximum. Okay, the number of B will be maximum. Thereafter it will start decaying. Okay, exponentially it will decay. So this actually represents the whole process very nicely or accurate. Excuse me. Whereas this one, you look, this will increase for some time, then it will be constant. No, it is not true, because B is again decaying in terms of this, some lambda 1 T. It is decaying, and for this, you know, for this process will not be so sharp. Okay, it will be not so sharp. There will be a time actually when the increment will be constant actually. Okay, so I mean to say, this is, see, there is a discontinuity. If you take the uh, derivative of that, there is a discontinuity here, but that doesn't occur actually. Any natural process will not be so that discontinuous process. There will be continuous process, because see, you have your B increasing, okay, B increasing, and from B0 it starts decaying. Okay, decay is happening, and see, if suppose you have production 5 nucleus per second, but you are having decay is happening. So decay depends on, see, decay depends on the initial number of nucleus also, right? So decay, suppose initially there was 5, then there will be 10, there will be 15, like that your B are produced, right? So your decay rate slowly increases. Okay, see, initially it was, suppose 1 into e to the power minus lambda into t. Okay, then you will have 15 into that. Okay, so this is actually, this term will be always, this will be, I think, yeah, since it is minus, so it will be less than B, at least you can understand that, sorry, less than B0, what was initial number. Okay, so I mean to say, so this is not represented because this is actually abrupt process, or discontinuous process, that doesn't occur actually. Okay, and this is not true, as I said, this will not be remaining constant because it is unstable nucleus. Okay, and this is, so option B will be the correct answer for this question. Okay, all right, so we'll move on to the next problem. Okay, so next problem I have not written here, I'll just write down here. Let me write down the problem here. So this is from electromagnetic wave chapter, the electric field of an electromagnetic wave. So this kind of question will come, at least one question will come from electromagnetic wave chapter, and very common question is this one, what I'm writing here. The electric field in an electromagnetic wave is given by E is equal to 50 Newton per Coulomb. This is the amplitude, is equal to sine t minus x by c. Okay, the energy contained in a cylinder of volume, the energy contained in a cylinder of volume V is, sorry, 5.5 into 10 to the power minus 12 joule. The value of V is dash centimeter cube. Okay, so you have to find out what is the V. So the electromagnetic energy is given in a cylinder. Okay, and that cylinder has volume V. So it is, so how do you solve this problem? This is very simple problem. Let me write down the energy density expression for the energy density. So what is the expression for the energy density for electromagnetic wave? You can actually write down U, small u is equal to half epsilon naught. Here epsilon naught is given. So epsilon naught is equal to 8.8 into 10 to the power minus 12 coulomb square per Newton per meter square. Okay, this is given. So half epsilon naught E naught square. Here E naught is given, right? So I can actually find out what is the energy density. Okay. So energy density, look, half epsilon, if I just put the value 8.8 into 10 to the power minus 12 and E naught square, that is 50 whole square. Okay, this is energy density. That means total energy, what is given here, total energy by volume, okay, equal to this. So if we calculate, this will be 4.4 anyway, 4.4, and here it will be 25 into 10 to the power 2. Okay, so 4.4 into 25 will give you 110. Yes, 110. This is 12. I'm sorry. So this is actually becoming 10 to the power minus 10. Okay. Now this is actually joule per meter cube. Okay, this is joule per meter cube. Let me tell you what is given. We have been given 5 into 10 to the power minus 12. This is the total energy. 5.5. I'm sorry. 5.5. So U by V is how much we have found? 110 into 10 to the power minus 10. This is joule per meter cube. Now if you want to find out what is V, then I have to divide this U with this. So this will give you meter cube. Okay, let me put the values here. 5.5 into 10 to the power minus 12 divided by 110 into 10 to the power minus 10. This is in meter cube. So this will give you 10 to the power minus 2. See, there will be 55101. See, 1. This will be actually 10 to the power minus 3. So this will give you 2. That means 0.5 into 10 to the power minus 3. This is in meter cube actually. Okay, meter cube. Okay, so we can have 5.5. Sorry, let me write just 5. 5 into 10 to the power minus 4 meter cube. See, centimeter cube I have to make, right? I have to make centimeter cube. Centimeter means 10, right? Of cube of that. So I have to multiply 5 into 10 to the power 6 to make it centimeter cube. That means I have 500 centimeter cube. Okay, so 500 centimeter cube will be the answer for this question. Okay, so what is the answer? 500 centimeter cube. Okay, so this will be the answer. So with this we have completed this particular paper. So I'll stop it here for today. In the next class we'll try to take some other paper for the discussion. So thank you for your patience. Bye for today.